So today's speaker is, good evening. Today's speaker is Professor Vladimir Rubtsov. You see the title of his talk, Two Valued Groups, Chazy Equations, and Quasimodular Forms. Volodya, please.
Это надо завше?
Ну, это можно сюда. Главное, чтобы этот колокольчик как-то... Нет.
А как?
Ну, вот заворотник запихни.
Вот так.
О.
Давайте заворотник. Заложим заворотник. Милое дело. Заворотник заложить. Так. Ну что, Осип, помоги мне, пожалуйста. В карман его так засунь. Ну что, я могу говорить, да? Good evening. I'll start my talk with a traditional phrase of thanks to organizers and people who are here, who are in the internet, just for this possibility to speak. And I'm sorry, probably my talk will be slightly non-structured because this is a unfinished project, ongoing project with Viktor Buchstaber and Mikhail Kornev from Steklov Institute in Moscow. And I will speak about absolutely different subjects. Historically, these subjects were not connected, and we discovered some strange and interesting connection between these subjects. The one object, it's two valued groups and algebraic structures around. Second object, it's Chazy equation. It's a kind of nonlinear ODE, which has similar to Penlevet property, but it is maybe the most famous third order Penlevet type equation, and theory of modular forms, which is of course a kind of parameterization, or if you want, solutions to conditions for both different objects. Anyway, this Chazy equation and two valued groups never were connected, and we observed it in a strange form. And this form is that the both are related to some associativity condition. And of course, there is another very famous associativity condition in 2D topological field theory. This is a famous Witten D-graph Verlinde equations. And of course, there is a very temptus will to connect the Chazy equation and structures of two and n valued groups with this associativity equation solution. And it seems that for at least for some examples of three-dimensional Frobenius structures, it is possible, because of this known link between Chazy and three-dimensional Frobenius polynomial and non-polynomial prepotential with one of part of it, it will be solution given by quasi-modular form of Eisenstein to series. So I will start with my plan. I will start with motivations. Of course, motivations are very personal. Why I was interested in this, and then I will give short account into the subject of my talk. So first, I will speak about two-valued groups, and Buchstaber polynomials. And then I will remind briefly something about Darboux Ifan differential systems, which are closely related to Chazy and Chazy equation. I tried to explain why it is interesting and why it worth to study. And then I will speak about quasimodular forms. And this will be kind of unification of these two subjects. And then, as a speculation, link to Witten de Graaf Verlinde equation and Frobenius manifold structures via the associativity. I'm not sure that I will succeed to speak about all these subjects, so I will stop at some point, and then if you are interested in to continue, I will continue. If not, it will be the end of my talk. Okay, so I want to remind you that fortunately, I spoke in this seminar about some things which relate to the first area about Buchstaber polynomials, but because it is the main and important for me today, I will remind what I mean under this polynomial. So the first reminder, it's about Buchstaber polynomial. In fact, it is a family of polynomials with three variables, x, y, z, and three parameters, a, b, c. A, b, c are arbitrary complex parameters, and the polynomials B family satisfies the following beautiful property. First, these polynomials are invariant with respect to all permutations of the variables x, y, and z. So, in fact, they are symmetrically dependent. And I can write this polynomial family in two ways. Explicit way, it's x plus y plus z minus b xyz in square minus 4 times 1 plus this parameter c xyz and times xy plus yz plus zx plus a x y z. So briefly, of course, you can write it in terms of symmetric functions. So it is e1 minus b e3 in square minus 4 1 plus c e3 e2 plus a e3. I just draw your attention that
What is
sir?
this E?
E are symmetric symmetric E1 it's x etc.
With respect to ABC.
No, ABC they are
It is symmetrical.
it's symmetrical with respect to three. This is polynomial family in CXYZ.
Yeah.
So,
Clear.
of course, you draw attention that I wrote this family of polynomials in a very specific way. It's a kind of discriminant type. So it's discriminant of some other polynomial. So this part of this polynomial looks like second. So you can write a discriminant of, sorry. You can write some other polynomial. Let's write it like a big P of t, and this it's a 1 plus c e 3 t square plus e1 plus b e3 t and plus e2 plus a e3. So if you take now discriminant of this polynomial, you obtain this family. And this is not absolutely, it is not non-important. But it is much more important that if you take this polynomial and write it in explicit way in XYZ, you will see that this polynomial family it can be written in such a form. It is quadratic in all variables with coefficients which depend on other variables. So you can write it in this way, you can write it in that way, or you can write it in the third way. All functions a1, b1, c1 depend only on x and y, and here only. And if you compute the discriminant of these polynomials, on X, Z, or Y, you will see that this family is so-called polynomially, discriminantly splitted. Discriminantly splitted. It means that, for example, discriminant in the variable z of this polynomial can be written like 4x cubed plus ax. It's a theorem. Very easy computational theorem, but theorem. Etc. So the discriminant of each variable is splitted in the product of cubic polynomials. And this is a crucial point. First, the appearance of these cubic polynomials gives you a very, very vague impression that there is a kind of elliptic curve behind of all this story. Behind. This is a just vague idea. And second, this property to be discriminantly splitted was described by Volodya Dragovich, former student of Boris Dubrovin, now professor in University of Dallas in Texas. And Dragovich proved that this property of Buchstaber type, he didn't consider it Buchstaber polynomial family, he considered another family of three variable polynomials in the framework of Kovalevskaya top integrability. And this property of these polynomials leads to separation of variables in this Kovalevsky top and integrability of this. So it is another story why it is interesting and important. Okay, then the next bunch of properties comes from the following. If you take the Möbius transformation, the simplest Möbius transformation in three-dimensional space, considering this, for example, like simplest transformation of this type, then the Buchstaber polynomial family transforms into another family of polynomials with some conformal factor, which I will denote by K, A, B, C, X, Y, Z. And this is a so-called Kontsevich polynomial. Kontsevich family. Why Kontsevich family is interesting? It is interesting because of many reasons. Because it's appeared in some enumerative problem in geometric Lagrange, But it is also, from the viewpoint of differential equation, it is very important family of polynomials. If you take so-called Hoyne equation, or very, very important and simple version of it, the degeneration of it, which I call two Bessel. It is also the subject which I spoke a lot about. Then one can write this differential equation of Hoyne-Bessel type like dt f dt plus f prime d partial, it's derivation over variable t, so it's a differential operator in t. F, it will be my cubic, monic cubic in t, sorry. And then the second term in this operator will be f prime times dt plus some term which doesn't depend on derivation, but depends on the coefficients of this cubic. For example, this is a second order operator, and if you take the problem, eigenproblem for this operator, you obtain solutions of these eigenproblems with eigenvalues lambda, then they are belong to this class of multiplication kernel problematic. It means that if you take eigenfunction of this operator in the point x, of this operator point y, then there is an integral formula for this over some cycle. I don't want to precise it for Hoyne now, with the kernel, and this kernel is explicitly one. Let me write more precisely. Z d z over z square root of this Kontsevich polynomial. For example, the simplest example, you know, because I spoke about it many times, it's so-called Bessel formula. For Bessel formula, this Kontsevich polynomial, Bessel L equal t dt square minus t for this operator, phi and lambda take equal to 1, phi x phi y equal 1 over 4 p integral minus x minus y, x plus y, and here you have phi of z dz divided by square root of Buchstaber polynomial 0, 0, 0 of x square, y square, z square. And here you have take dz over z. This formula is a version x should be bigger than y. So you can write here x minus y. And this Buchstaber polynomial with 0 parameters, it is x squared plus y squared plus z squared minus 2 times xy plus y z plus zx. So this is so-called here this Buchstaber polynomial in squares, and here just I wrote it in, and this is a
for the first case, consider polynomial with arbitrary parameters.
yes, with it is generalized Kontsevich polynomials with 3 parameters, which comes from this ABC here.
Yes, but there is no ABC on the left-hand side.
C, yes, ABC, there is ABC in this because I didn't write the function. Here I can write the function explicitly. This is a Chazy function. I told you a lot about it, but I will speak today again about Chazy function. This solution phi for Bessel, it is analytic, one of two solutions, which is holomorphic. Second solution has a logarithmic term in representation. And here also for, I can't write explicitly, but it depends on ABC, it enters for this Hoyne equation. And of course, one can write very, very explicitly, one can write Riemann scheme and choose Hoyne equation parameters. These parameters will be entered in this ABC because Hoyne operator contains this ABC in F and contained in this term which I didn't write. It is not.
Let's proceed.
Yes, because it's yes. So you see, it is an interesting object. It is an interesting object. Of course, the next question: if I take more complicated, but not so much. For example, if I take one of Buchstaber polynomial parameters non-zero, and this also I should say a few words. I take A non-zero and 2 zeros. In fact, there is a similar formula for first of all, there is operator, and this operator has eigenfunctions are 0 in 0. So this is also I0 I0 modified Bessel solution, and here 0 index Gegenbauer polynomial. I will not write this, but I will write the Buchstaber polynomial. It will be the same like here. But this parameter A gives you cubic term. And I want to say that this polynomial and this polynomial, Buchstaber discovered when he studied the formal group structures for usual cohomology. and this for K theory. Of course, if you take the next interesting case, it will be 0, G1, G2, G3. I will denote these parameters by G2 and G3, not by any chance. So this polynomial, you can write, so A equal to 0, it means that you have X plus Y plus G plus G2 XYZ. Let me write it in E1 plus G2 E3 in square minus 4 1 plus G3 E3 and then E2 because the first equal to 0, so this is the form of this Buchstaber polynomial, and this Buchstaber polynomial with 1, 0 and 2 coefficients G2, G3 gives the this also describes a formal group structure associated with the elliptic curve. Namely, if you make the following change of variables, which is similar to this Möbius transformation, take x big, which is 1 over p function of x plus p function of some alpha, and y the same p of x plus p of y plus p of alpha, and z equal 1 over p of z plus p of alpha. Then using the addition formula for p function, you can write the formal group structure associated with this polynomial like simple addition of this transformed, like just linear addition law. So you have non-unique, and this addition law is two-valued because of this plus and minus. This is very beautiful story. We wrote about it, a paper with Buchstaber and Ilya Gayur. It is published in the first volume in January of Izvestia, of Russian Academy of Science, but it is a little bit apart. What is the alpha? Alpha is the point in the elliptic curve, and this elliptic curve has a Weierstrass form with these coefficients G2 and G3 like modular coefficients. G2 and G3 also expressed in terms of squares and cubes of p alpha. I will not write explicit formula. You can find it in our paper, if you want. So this is old, more or less. I told about it in different circumstances, but there is a new observation. This new observation is the following. If I take this Buchstaber with 0 parameters and take square of it, like in the formula of Besset, I will keep now notation like Cherin function. Then this is the first integral of a system, differential equation system, which is a reduction of self-dual Young-Mills in 4 dimensions. This system people call Darboux-Alphand system. And Darboux-Alphand system looks like this. You have 3 unknown functions in time. Omega 1 dot equal to omega 2, omega 3, like in the case of usual top. But also there is another quadratic term. It's omega 1 times omega 2 plus omega 3. And 2 other cyclically similar. 3, 1 minus 2, 3 plus 1, and 3 dot omega 1, omega 2 minus omega 3, omega 1 plus omega 2. It is not exactly the first integral of this system. Moreover, this system has no algebraic first integrals, only transcendent. But this is the first integral of some intermediate system, which is a system for so-called Taylor-Einstein invariant, SU2 invariant metric. This matrix in 4 dimensions, well known, and relates to these Alphand variables like this. You take SU2 invariant 1 forms, sigma 1, sigma 2, sigma 3, and the system of sigma 1 equal sigma 2 with sigma 3, and etc. And then the metric which Cartan equation SU2 invariant, it is a Kähler-Einstein metric G, which is omega 1, omega 2, omega 3 times dt square plus omega 2, omega 3 over omega 1 sigma 1 square plus cyclic. So you have sigma 1, sigma 2 square, sigma 3 square, and coefficients are this. And these are unknown functions of time, which should, in some reduction, satisfy to the Alfvén system. Why I was interested in this? First, because I have this first integral related to Buchstaber, and second, I know from another source, and this source is well known since early 90s, that the solutions of the Alfvén, for example, if you have solution omega 1, omega 2, omega 3, take its sum, denoted minus 2 times this, and denoted by y, then this solution omega 1, omega 2, omega 3 of this system implies that y satisfies the following equation. And this is the famous Chazy. This is the famous Chazy. What I can say about Chazy? I can say something. I didn't write it, but it is. I typed today, but didn't write by hand. First, I can write how this Buchstaber or Chelin relates to this. Just. This lambda is a scalar curvature of the metric G, this metric, which can be written in X like this. So X, Y, and Z, this coefficients, this is X, then, so this coefficient is X, then the next is Y, and etc. So it is the same, so it's X squared, and here also, and here no, if you write this like this, then XYZ in square, it is just a product of omega. So this explicit relation of Buchstaber or Chelin to the metric which solves by Alfvén. And property.
So I see to understand. So you wrote the Chazy equation. Then what
Chazy equation, it is a consequence of solution of Alfvén system.
Okay, but what is this lambda, and how does it relate?
Because there is, initially you have this famous Einstein-Keller field equation.
No, how lambda relates to, I mean, the function lambda. How does it relate to?
It is the first integral.
It is the first integral.
It is the first integral,
Okay.
and it is especially very important when this big scalar curvature equal to 0. Then you have the so-called Ricci-flat case, and in the Ricci-flat case you have hyperkähler metric. And it is important. It was Atiyah and Hitchin discovered as a special case. Anyway, what I can say about the solutions of Chazy, because this is the next link to what I want to tell you. It is easy to check that there is an interesting Backlund transformation. If you take gamma from PSL to C, or just take SL to C if you want, and then you can write gamma. It's like A, B, C, D. Then on this group acts on Y and on omega 1, omega 2, omega 3. So let's write omega Y like this. It is 1 over C T plus D square omega Y of AT plus B CT plus D plus additional term C over CT plus D. This is transformation says that these omega i's are quasi-modular functions of weight 2. And the property of Chazy and Alphand Darboux that this is again a solution. So omega I are solutions of, and gamma of omega I are solutions. Please. Okay? Okay. Now, again, some reminder why it relates to some associativity and algebraic structures. So I'll stop at the moment to speak about Chazy. I will come back to it, but not now. And the second part, reminder about what I can, probably what I can. Just for those who never heard or forget, two-valued groups. What is a two-valued group? It means that we have some multiplication structure on a set X. Take Cartesian product of X with itself, and this structure we will denote by star. Take element X small, Y small from X, and obtain a two-set of couples and as element of symmetric square of X. So this operation I will call a any set. Any set.
What is symmetric square of any set?
No. It might be, I don't know, algebraic object, for example, algebraic variety. Why not? You can take a curve, you can take a surface, whatever.
What is symmetric square of a surface?
Symmetric. It's you have Cartesian product.
Yes.
And you have a set of pairs.
Yes.
With independent on the order. What is symmetric product? For example, if you have a differential operator and you have a solution, then you can take space of the solution. Then you can take solution symmetric product of this it's a operator, and solution of this operator, they are products of all solutions of the.
So you mean you act by Z2 on this Cartesian, and
I have X and Y, and as I assign to this pair XY two set two element set.
This I understand. I don't understand what is symmetric square.
What's the difference between if you take X and X, you have pair X and Y, and X and Y depend on what, and if you
they depend on nothing.
If you consider.
So it's quotient with respect to
Yes.
Z to X.
Yes. And I need to impose some axioms. So it is two-valued group operation if I have some multiplicativity, associativity. It means that if I have three elements from X, then I have product. I will call it product in this order, and I have the product in this order. And under associativity, I will understand the coincidence of four-element set. This is a four-element set.
But just a minute, just a moment. Just a moment.
Mm-hmm.
Your star is defined on Cartesian square.
Yes.
But the result doesn't belong to Cartesian.
Associativity is in this. Associativity is a condition in this.
No, but this operation, X, Y star multiplied by Z, it is not defined.
Why?
By your definition.
No. But I assign it. Yes. So to x times z and to y times z, I assign two element set. So I have I have 4 element set.
X star y does not belong to x.
X, Y star doesn't it belong? It is a coincidence. It's the elements here, and then from this I take.
No. I speak about your associativity formula.
Yes.
You multiply x by y.
Yes.
And obtain something, and then you.
No, I have a 2 element set, and each element of this set I can multiply again. I have each. So it is in.
No, but it does not belong to x. Each element of this.
But
it belongs to
okay.
The quotient. You told that z.
You mean that it is symmetric? Yes.
Yes, but this operation is not defined.
Why?
Because star acts on 2 elements of x.
But if I take, okay, I have this sim. It is again a two element set. I don't understand what.
I don't understand. You told us that star acts on 2 elements of the x category.
I will give you just example. You will understand.
No. I don't understand. I don't understand definition.
No. You will see what I have in mind, and you will see how it works. Let me say that you need also natural element. A natural element gives you 2 element with 2 element identical here. That's what means that E is a unit. And also you need x minus y element. And this is very tricky. You have coincident 2 element set, and it should, one of the elements of this 2 element set should be E. One of element of this set should be E. So this is a definition. You will see the example. I don't understand your opposition. Again, let me.
These Z1, Z2, they are not elements of X.
Let me.
But well, for example, let me understand the definition. These are not elements of X. They are elements of quotient. By your definition, they are elements of.
The symmetric square, it is also a pair of elements. You agree? Symmetric square, it's again a set of pairs.
Yes, but not of elements of X, but of their classes.
No. Class is just pair, but each element in this, it is element of X. And I can take it and take the product. Also, again, class, it is the element of sim square. So this is a class, but each Z1, Z2, it's element of X. And I can separately take Z1 of, I don't know, Y, for example, and Z2 of Y. And I have another couple of elements, and I have four uple of elements. Why?
Because it is a class.
Class is I can take the element X.
Yes, of course.
Yes. And what?
Because Z1 and Z2 are the same in your definition.
Well, I don't know how except the trivial example, I don't know how to explain it to you. Let me, I'll do the trivial example, okay? Let's take X, C, and it will be just abelian group with respect to additivity, okay? And I have order 2 automorphism. And then I take the C factor by Z2, the quotient, okay? And this will be my X. I put it X still, and this is my X. This will be the initial object. And now I take a class, like you see, and put the element. The statement that if I take x minus 1 equal to x and equal to 0, then I will obtain two-value group. Elementary two-value group. Do you want to take the associativity condition? I will write it if you want. This is Z1 and this is Z2. This definition is not occasional. It is a definition of the roots of this quadratic equation with respect to Z. So Z1, Z2, it's easy to see that Z1 plus Z2 equal to x plus y, Z1 times Z2 equal x minus y squared. If you solve this, you obtain this. Now, let me check the associativity.
May I make a remark?
Yes.
So, your star acts from here to now you write your associativity. X X X star, the first star, well, we're here, and we don't have a map. You didn't define it, and then from here to please define it.
No. I don't know what do you mean that X.
Well, you told us that.
No. Here I understand it.
No.
Here I understand it.
You
But
give us
no.
definition.
No, yeah, I told you the definition that I have all non-ordered pairs. That's all.
You told us that this is quotient by the action of
No. It's quotient here. It's yes, but here no Z2, no Z2.
What example? Give please the definition.
No, here it's not Z2.
But
What
you identify pairs with elements. Then give the definition. What is the target of this map star?
Okay, I will. I will give you formal definition if you want, like this. I think I supposed to do. Oh, okay. So let's see this. Let me do this. So let me have X times X. We have X times X by automorphism order 2. Okay. So let's denote this by P. Okay. Is it defined or not?
Yes, of course, it is quotient.
Okay. Okay. So now I want to define the star. And I define the star like this. X star Y equal to P here X say tilde times Y tilde, and I have the action of automorphism on
what is tilde and what is dot? What is tilde?
Just a moment. So let me this A, it's action of this automorphism on Y. And X tilde, it's P minus 1 of X. Y tilde, it's P minus 1 of Y. And so and
dot.
Dot is I suppose that X is the group, usual group. It's I just want to take the very precise case. I take usual group operation, and I define a new operation. Okay.
So you don't have a definition of arbitrary two-variable group.
I have, but let me for my aims I need only this, just to skip this discussion, because I don't want to write the diagram. Okay. Is it okay for you?
Well, then we work with, we define two-valid structure on a classical group, yes?
No. It's on the classes of, we define this structure on the classes.
Yes, yes, but the initial object is
it is what people call cassette construction. It's cassette construction. It's a special two-valued group. Say, that's what I need.
Yes, proceed.
Okay, so
by the way, is it well defined?
yes.
Why?
What is not well defined?
Well, you took inverse image of x and y.
Well, you want me to check this correctness now? I think that I have 25 minutes. I will. You will see that it is correct in all. No, but okay. What do you want me to correct? No. Stop. Let's do. But it is just absolutely spent of time.
What is strange? Pi know
What?
nothing about the group structure, and then that's why I.
It's a projection.
Yes, of course, it's projection.
Okay. So what you want me to check?
That star does not depend on the choice of representative. And if pi knows nothing about the group structure, it's strange.
Is it a group? And this is also quotient by automorphism.
Yes.
Yes? So this is a homomorphism. Or not? Joseph.
This is a group of.
Yes.
Okay.
Okay. It's what we need. In fact, we need what to say. What is the natural element? And natural element, it is just image of the natural element of this group. And inverse, of course, it's just p of x minus 1. Now everything is correctly defined. And this is typical example because here you have additive group structure. Here you have our x, and then you define this two-set two-element set. Then to check associativity, you need to take the coincidence of polynomials. And I put it also, especially here. Yes. Let me take this z1 of xy. It's equal to square root z2 xy. And then associativity condition is the following equality which we need to check. It is t polynomial with some variable t minus z1 of z1 of xy z. Yes. Times times it should be 4. Oi, t minus z1 z2 xy z times t minus z2 z1 xy z times t minus z2 z2 xy z equal. Now in opposite side, in opposite way, you take t minus z2 z1 xy z times t minus z2 z2 xy z. So it was z2, now t minus z1. That's Benno. So coincidence evident because it is just the same elements in the same elements in the polynomial rings. So this guy, it is here, and etc. Well, now it's enough to check also that this is a good definition. Well, it is easy arithmetic that these elements are inverse and neutral for this two-valued group, elementary two-valued group. But what is interesting? It is interesting that this definition comes from this quadratic polynomial. And this quadratic polynomial, it is exactly B0 xyz. And what about the other polynomials? Other polynomials defined also two-valued structures, two-valued group structures, but in more complicated context. For this, I need to say a few words about formal group. Formal group structures is given by a series over some ring R and I will speak about R. It is R, C, Z, whatever you want at the moment. For me, it is important Z and C. So first, if I take V equal to 0, and this series should be U. And second, if I take F and U and put F, V, W on the second place, it is the same series like phi of U V W. If I have these two properties, then I'll say that this function series of V define a formal group. The simplest formal group plus V. This is a formal group which discovered in cohomology, and this corresponds to this equation of Buchstaber. He proved that it's a theorem that the elementary two-valued group like this defined this simplest formal group in the following context. I will explain. And the second example, it's U plus V minus Q V. That's what people called K-series formal group structure, and it corresponds to cubic term with Q, which I wrote before. Okay, how these polynomials define this formal group? This is also interesting construction. It is called square module two-valued formal group. So these both are square module valued. Let's suppose that we have some formal group, phi, any formal group, usual group. And then let's consider the equation z squared minus theta 1 of xy z plus theta 2 of xy equal to 0, where theta 1 and theta 2, it's, well, formal series in xy. Then let's consider this like equation in formal series and take two roots, z plus and z minus, roots in this formal series equation. Then the construction
We assume that the solutions are also formal series.
yes, it's this formal series, of course, z plus z minus should be equal to this theta 1, and product should be equal to theta 2. Now we take our formal group and suppose that it is over C. Then we can take value of phi in U V and take phi in U bar and V bar, where bar are just complex conjugation. And this we, of course, it is module square, and we put it Z plus And then we take phi u bar v, phi u v bar, which is phi u bar v module square, and we put it z minus. Then we have two-valued group, like we had it just by this two-valued formal group. So we have element x, big X, from our series and y, and have this z plus and z minus. The theorem which Buchstaber proved that if we take this u plus v like phi, and then this we have Buchstaber polynomial.
Just a moment. What are these x and y? What are these x and y?
X and y, it's a...
You wrote capital X and y, and who are they?
No, they are series. We have formal series. Now we have just a group, and we had a formal group, and we have two-valued formal group. It's a two-valued.
We took x and y. They are series.
Yes.
Two formal
and
series.
Here we have a set of two series. Z plus, they are series also, and Z minus also. So we have a set of two series.
Yes, this I understand.
Okay, just to finish, because I have 10 minutes to.
No, I still don't understand.
What?
How z plus and z minus are related to x and y? X and y are arbitrary formal series or not?
X and y, no, they are small x and y, they are variables. Or you speak about this?
These ones, yes.
No, it's an element of from R.
Yes. So, and how these elements are related to z plus and z minus? I took two arbitrary formal series, yes?
Yes?
And what do I do next? How do I
Now,
find z plus and z minus?
you take this.
Yes, but we have no z, x and y capital here.
Why?
Where are they? Explain me. In all this construction of z plus and z minus, there are no x and y capital.
Okay,
now
maybe.
You took arbitrary x and y.
No. I took just a moment. Theta is series in x and y.
Yes, this I understand.
Yes. So z are series in x and y. Yes.
Yes, small.
Small. the relation is here. So this we have the product of phi in u and v.
Yes.
Yes. So
no x and y capital. Maybe this is a product of theta 1 and theta 2.
why theta 1 and theta 2? Theta 1 and theta 2. No. Theta 1 and theta 2, they are these guys.
Yes.
So if we take
X and Y live in one universe. Z plus
just a moment. I'm a little bit confused.
And they know nothing about each other.
No, they know. It's like in the usual multiplication. You have product x and y equal to z1, z2, two roots. So this z2, z minus, they are roots of this equation.
Yes.
They are
now
roots.
I take x and y capital, and you define their product. Then I took another x and another y, and the product will be the same. I took two zeros, and the product will be z plus z minus.
Sorry. It's product. It should be. So we have this zero. Yes, this is the of course, it should be two times x plus y, and here should be x minus y squared. Okay, so this is 2 times x plus y. This is x minus y squared. So this is a Buchstaber polynomial with zeros. Okay. So now we have this guy, and then we have z plus equal to this module. Let me write u plus v u module square plus v square plus 2 times not 2 u v bar plus v u bar, and this should be 2 times x plus y, and the same for z minus.
Well,
it should be product for x and y, new product for x and y.
But they should be related to x and y.
But they are related.
But where?
Here.
Where x and y? Capital.
Capital X and Y. Good question.
You took two arbitrary formal series and then constructed a very particular pair consisting of Z plus and then Z minus.
Mm-hmm.
In no way related to X
No,
and
no, no,
Y.
it's related like this. It should be like this. It's a square of plus V. No. Let's see like this. I understand, Osia. In these examples, X and Y, it's a small X and Y, because you see in this case, this series, it is just.
So it's not
Yeah, it's my
a group
fault.
structure on the
No,
set of
set of
formal
series. No,
It is not.
no, it's set at on C. On C, it's a new group structure on C.
Yes, but the right-hand side should be symmetrical square, as you taught us, of C.
Yes, you have C.
Yes.
And then you have this quotient by conjugation. So this construction uses
Z plus and Z minus are formal series.
But these are, in this case, they are formal series, which are trivial formal series. They are just U plus Y, and that's all.
So this is not a general construction.
No, it's a general construction.
But it has nothing to do with formal series.
But nothing to do with here, not formal series.
Yes. No formal series.
No formal series, just numbers.
Yes.
Well, classes, not numbers, classes of. It's my fault. I'm sorry. Just classes of numbers. Yes, I was a little bit over.
Okay.
Yes. No, it's just. Of course, it's a product on C. On C quotient by conjugation.
And why then all this tale about formal series?
Because you can take also formal series for this. You can take, for example, you can take instead of U plus V, you can take what you can take. You can take formal group more complicated, like this. It's a theorem, but I never check it. It is universal construction for formal series as well, but the product is in the numbers.
Okay, so it's in classes of complex numbers.
Yes. And you see, it is sometimes this product can be extended to CP1, and sometimes it is a product which can be lifted from the addition law on elliptic curve. But this you should take another theta 1 and theta 2. it's a simple object, but with very tricky property. For example, there is an analog of exponential map and logarithm for this group, like in the usual Lie group, but it is given by formal series. This logarithm.
Yeah, of course, this understandable.
This. We just only yesterday understood how to write exponential and logarithm for this simplest u plus v even, and we understood how elliptic curve appears.
So you can construct a formal Lie group.
Yes. Something like formal Lie group. Of course. And it is not easy formula. If you want, I can write it.
No, I think it's not necessary.
No, it's a.
I understand. You write something like Campbell-Hausdorff, and this will be a formal two-valued group structure on formal series. Yes?
The theorem which was proven many years ago that all possible groups of such type, they are isomorphic in the class of two-valued groups to this elementary group. And this exponential map established the kind of map from this elementary group to non-elementary. And one can write differential equation if you want for this exponential or for logarithm.
And now, we forget about. You promised to come back to Chazy equation.
Yes.
Yeah.
The Chazy equation is very nicely. There is a property which I mentioned, that Chazy equation has modular behavior. It means that action of SL2C on solutions of Chazy. And up to normalization, there is a solution which is proportional p square. Oh, just. There is a normalization. Yes. P square over 3 E2, where E2 is a quasimodular Eisenstein series form, which is Eisenstein series. So E2 is equal. Oh, this again normal.
It doesn't matter in particular form, but why is it important?
It is important because you can now you can take all. For example, you can take derivation of this solution, you can write some where my here. You can write some potential that's what I didn't have time to say. When you write the Buchstaber polynomial a, b, c, x, y, z, these a, b, c parameters, they can be expressed and in parameters, so they define a two-valued algebraic group, like like 0, like 1. It is possible to define this two-valued algebraic group associated with elliptic curve y square equal like this elliptic cubic. And now we can single among all these algebraic two groups so-called symmetric two algebraic group. This is the theorem of very recent theorem of Buchstaber and Kornev, and they expressed these coefficients A, B, C for symmetric two algebraic groups like this. It's K2 over 4 minus B. It's K4 over 2 and minus C. It's K6 over 4. And these coefficients K2, K4, K6, initially they are numbers like A, B, C. But there is a relation between them in the polynomials of with generators K2, K4, K6. The relation is the following: K4 square minus K2, K6 equals to 4K8. And Buchstaber and Kornev proved that all these symmetric two algebraic groups, they are defined over polynomial ring from K2, K4, K6, and K8 modulo this condition. And this condition, it's associativity of this symmetric group.
Okay, how does it relate to Chazy equation?
But what I discovered that such relation, it's a typical relation in quasimodular group. So now, instead of constant or formal generators, I propose to consider some point tau in upper half plane and consider these functions, these generators, like a function of tau. And the relation among quasimodular forms says that K2, it's proportional, let me say, up to normalization, to E2. K4, E4. It means to G2 for corresponding elliptic curve in Weierstrass form when we change the variables to kill this second term. K6, E6. K8 doesn't exist as a because it can be expressed in terms of this quasimodular form. If you consider modular form of weight 8, it is one-dimensional. But if you consider quasimodular form of 8, weight 8, it contains this relation. So it is very plausible that it is very natural to consider these parameters like parameters of tau. And then you have a curve in the space of these coefficients, and you have a curve in space of coefficients of Buchstaber polynomial. This condition, it's condition of associativity. And if you write Chazy like this, then all other E6 you can express in E2, E2 prime, and E2 double prime. And then you obtain the solution of Chazy. So this solution of Chazy implies associativity and vice versa. That's what my observation. Associativity condition implies Chazy.
The only thing you need from this equation that this Eisenstein series is its solution. That's all. So
yes.
Essentially,
not only. No.
What else?
What else? Now, of course, I was not very happy because it's too simple to use this. But I read Dubrovin's paper, and in Dubrovin's paper, he proposed a three-dimensional Frobenius manifold. And in this three-dimensional Frobenius manifold, he finds potential some coefficients and this F is a solution of VV if and only if this phi is a solution of Chazy.
Well, it's quite another topic.
No.
Why not?
It's a long story. But anyway, it's not another topic. This is a solution. This phi, it's Chazy. It is associativity in two different senses. In sense of two-valued groups and in sense of Frobenius structures. So solution of Chazy gives associativity in two different senses. That's the point. Why it is not another topic? Because to construct this solution of VDVV, you need some flat connection. And this flat connection relates also to this relation. This relation also defined a kind of Gauss-Manin connection on the elliptic curve.
Okay, I'm afraid we have to finish because
It is in progress right now, but we are pretty sure that we can write condition of flatness for Gauss-Manin for elliptic curve as a solution of Chazy.
Okay, thanks a lot. So I'm afraid that there is no time for questions. We meet in a week again in this room. Goodbye and thank you.